My name is David Thompson, and this presentation is Local Methods for Pattern Recognition. It's the first of several modules that will involve or talk about dimensionality reduction in the context of this Caltech Big Data Summer School. And so the first of these lectures is intended to provide just a common reference, a basic skill set that we'll refer to later. I'm going to review some basic pattern recognition strategies, such as classification and regression, that you will have been exposed to previously, but I think it's worth talking about them again because it really is foundational for some of the things that we'll describe later as far as dimensionality reduction is concerned. So it's an important background to have. Okay, so this first talk will, as I said, review basic pattern recognition problems, classification and regression, and in particular in the context of local pattern recognition strategies. These are non-parametric pattern recognition strategies as opposed to, say, parametric methods that we've seen earlier. A lot of these fall into the general category of nearest neighbor methods. So I'll describe the nearest neighbor methodology and why that might be a good thing. And then a couple variants of that, including local linear regression, which is a flexible regression strategy that is based on a local non-parametric approach, and then kernel density estimation, which is a probabilistic method for pattern recognition. Okay, so let's start off with a simple pattern recognition task. Here I've got a data set with a couple of attributes on it, and as pattern recognition folks are wont to do, I've just plotted these, giving each its own coordinate. So here this is a two-dimensional attribute space where every data point may have associated with it some class value or some real valued ordinate that we're regressing against, some value that we want to predict. Or perhaps we're just interested in intrinsic properties of the data set, how the data is distributed, to try and infer something about the process that generated the data. So that's more akin to, say, a density estimation task where we're estimating probability density in this two-dimensional attribute space. So there are lots of different kinds of pattern recognition questions that we can ask of this data set, even this very simple one here. So I've plotted here on this slide a red question mark to indicate some query point where we'd like to describe or predict the behavior of this process. And again, this could be a prediction of the real valued function at that location in the input space, or it could be that we have a new point there whose class we're trying to infer. Regardless, we've got a query point and we want to be able to infer something about what the process is doing at that location. All right, a little bit of notation, background. So I'm going to treat these data points as column vectors. So we're going to say x sub I is our data point, and it has from 1 to n attributes. Again, this simple example only has 2, but you can imagine having arbitrarily many. And because this is dimensionality reduction, we're eventually going to be talking about data points that have hundreds or even thousands of attributes. We can represent the entire data set as a matrix where we stack these column vectors together in rows. So we have an n by d matrix where d is the number of data points. And for now, without much loss of generality, I'm just going to assume that all these attributes are real valued continuous attributes. So I'm not going to deal much with, for example, categorical attributes, but many of the same principles that I'll discuss apply to categorical attributes as well. And you may be familiar with encoding strategies that you can use to turn categorical attributes into continuous. So really we'll just focus on the continuous case here. Okay, so one reasonable way to do pattern recognition on this data set is to just look at the local behavior in the vicinity of the query point that we're interested in inferring. So here this goes under the assumption that whatever process generated the data is locally smooth in the input space. So maybe we can disregard a bunch of the points that are really far away from our query, right? We don't have to look at the function values at the extreme lower left side of the plot. We can just look at the values in the upper right near the red question mark, right? So maybe look at its closest neighbors to see what the function is doing in that vicinity. And you can do this for each of the pattern recognition strategies that I mentioned. All right, so the canonical example is, of course, nearest neighbor classification. Want to infer the class of the query? Just look to its nearest neighbor in our data set and assume that it has the same class as that one neighbor point. So in this case, I've indicated with a red arrow the nearest neighbor of the query, and so we just assume that is the class of our query. Now, this amounts to a Voronoi partitioning of the input space. So here in 2 dimensions, I've partitioned the space, drawing areas for which every input point is responsible, right? So you can see that nearest neighbor point is actually responsible for a polygon within this input space, and any query within that polygon is going to get its class. Now this has kind of a nice property because the data that is, where we have denser data, right, in the center, where we have more information, the Voronoi partitions are smaller, right, and we permit the function to vary a little bit more. Far from the data cloud, these partitions get a lot larger, and again, we don't have as much to say about that corner of the input space, so our inference there is going to be smoother. Right, so this is a basic example of nearest neighbor classification. And the decision boundary looks like this. This is the resulting decision boundary. I've applied here some labels to the data set, red and blue. And you can see that the decision boundary here drawn in black is sort of a wiggly shape through this input space that bends around all of these inputs. Now the query has actually been paired with a blue point. This is kind of interesting though, because if you look carefully, you'll note that the query is actually also fairly close to a bunch of red points as well. Right, to its immediate left there are clusters of red points, and it's almost as close to those, but it's just sort of happenstance that it got paired with the blue point. Another way of saying this is that the one nearest neighbor approach to classification is rather sensitive to noise. It has high variance in the language of pattern recognition. The variance bias trade-off is definitely, it's definitely more variance than bias in this case. So this also manifests as a fairly wiggly decision boundary. So if you see in the center of the cloud there, maybe our decision boundary wiggles a little bit more than is appropriate given the amount of data that we have. So what this really needs is some way to smooth that decision boundary or regularize it so we're less sensitive to those single point outliers. And the way that's typically done is by introducing more nearest neighbors. So here I'm looking at the 5 nearest neighbors and taking a majority vote of which class to call the query. And you can see the decision boundary straightened out quite a bit as a result. This has the effect of regularizing or smoothing our classification, and we're now paired correctly with the red points as opposed to that single blue outlier. Right, so this is just one example of regularization in the context of pattern recognition. So I alluded to other kinds of pattern recognition tasks that one might want to perform using this sort of local estimation, and another one is regression, right? So a really simple regression strategy that's sort of the regression analog to k-nearest neighbor is kernel smoothing. And that is if I have some real valued function that I want to estimate, I can just perform a weighted average of the of that function where the weights are weighted by local neighbors, right? So locality to the query point. Which amounts to convolving a kernel function over the training data. So here the kernel function, which I've represented as k, can be any decreasing function of distance. So it's quite common to use a Gaussian bump for that. There you see in the lower right the formula for a Gaussian kernel function, which is a perfectly good kernel, and it's actually what I'd recommend you start off with as sort of a first cut for all your kernel smoothing problems. It's got a free parameter, which is the width, which is here represented as h. So if the width is wide, it's sort of akin to many nearest neighbor classification. We're taking into account a large neighborhood around our query point, right? And most of the nearest neighbors in that point's vicinity will get more or less equal weightings, right? So that's a lot of smoothing. If our width is very narrow, then what that means is that it's a very skinny Gaussian bump function, and we're only looking at the points very, very close to the query point. So it's akin to a 1 nearest neighbor where our variance is a little bit higher, which might be more appropriate if we have more data, for instance, or we're in a dense region of the input space. Note also that we're normalizing by all of the kernel outputs over all of the data points. So we do this calculation over all the training data for any query whose value we want to estimate. So here's an example for just a 1D classification problem of what kernel smoothing looks like in practice. So we've got a process which is green here. It's y of x, which is just a simple periodic function in this case. And it generates a bunch of data points that are here noted in blue. And we're trying to infer what this function looks like, and have applied a kernel smoothing algorithm to the data. So we can see that for x sub naught there, where we've inferred a value y of x sub naught, or y hat, because it's an estimate. And you can see we're looking at points in the vicinity of x sub naught to determine what that real function value would be, and that those points, which are red in this diagram, are weighted by a kernel function which is centered on x sub naught. So points near x sub naught are going to get high weighting in our local average, and points far from x sub naught are going to get low weighting. And that's what the yellow Gaussian function there represents. So you can see that this is, without very many assumptions at all, just using the intrinsic properties of the data, this method's already done a pretty good job of modeling the periodic sine function. Right, so this is quite a powerful method for regression, simply because it makes so few assumptions about the intrinsic structure of the data, the parametric form of the data, and can be used just out of the box in a wide range of problems. But it's not perfect, and in particular, you'll note challenges at the edges, right, where there's a little bit of bias. The function sags a little bit at the edges instead of modeling the data precisely there, and that's because we're being unduly weighted by the data points on one side of that function at the very extreme x values, on the extreme left and extreme right. So we aren't doing as good a job of modeling our underlying function there. And there are ways to address this. A common way to do that is by adding a little bit of parametric inference into this, by building in into our instead of using a local average, actually use a local linear regression that takes into account the linear structure of the data set at those edge points. And this is what local linear regression looks like. It's actually very similar to kernel smoothing in a lot of ways, but it builds off of standard least squares linear regression. So you may be familiar with the hat matrix and standard linear least squares. Here's an example of a linear least squares estimate of x sub naught, where we've defined a data matrix B and our predictors y. Right, so this projects the data onto the column space of the design matrix B is the basic premise here. Now, if we add kernel weights to this, right, so that we weight our nearest neighbors more highly in this regression, we get an expression that looks something like this. So we've added matrices W of x sub naught, right, which represent the kernel evaluation of all of the data points to the location x sub naught, right? And so that's a diagonal matrix with all the kernel weights on the diagonal. So just by making this simple change, we've actually created a local linear regression problem that will let us predict the value of this function at x sub naught. And this is what it looks like. And you can see it does a very good job of modeling our sine function. And in particular, it's removed the bias at the extremes, the extreme left and extreme right. So we're actually modeling the local linear structure there quite accurately. But otherwise, it's very similar to kernel smoothing. Okay, there's one more local method for pattern recognition that I'd like to talk about, and this is kernel density estimation. So this is meant to address the density estimation problem. So if we want to estimate a probability density or a conditional probability density in this input space, one way to do that is simply assume that each input point is responsible for a local kernel, right, a local probability density function in its immediate neighborhood. So we can take the density to be the sum of all, or the density at any new point to be the sum of all the kernel evaluations of all our training data. So this image here at right shows an example of that. We've got just one real valued input here on the x-axis, and we've convolved our kernel across that, right, and summed up the responses of the kernel over all of those data points to provide some estimates of the density. Now here the true density is given by the gray curve, and the estimated densities are given by the various color curves. As we change our kernel bandwidth, you can see that the density estimate becomes smoother or more wiggly, right, which is tantamount to the regularization that we saw before, both with the increasing the number of nearest neighbors or changing the bandwidth of our kernel smoother. We can do exactly the same thing here. Note that the blue might even be a little bit over-smoothed, right? So we're doing a pretty good job of modeling the underlying Gaussian function. But we've started to truncate its peak a little bit, right? So maybe a width of 0.3 is a little bit too much. One thing to note about this expression, note that it's normalized to provide a true probability density estimate. So it's a valid PDF. So that the normalization factor Z normalizes our kernel function so that all of the kernel evaluations have volume 1 or area 1. And we're also dividing by the total number of data points that enter into this kernel density estimate. That's the N score. So our density, if we were to evaluate the density everywhere in the space and integrate that, we'd get an area of 1. Okay, so how do you go about setting all of these regularization terms? Well, typically you'd simply use cross-validation. So you could use you could leave one point out and look at your performance estimating that point for either regression or classification, and use that to adjust the kernel bandwidth, so the number of nearest neighbors. That's probably the most common way. I guess the analogous method for density estimation would be to look at the likelihood of held out data points, right? So cross-validation is the typical way that one would estimate these parameters. But fortunately, there's really only one parameter to estimate, which is, in this case, the kernel width. So we get a wide range of very flexible functions out of very few input parameters. We're letting the data speak for itself, unlike a parametric method. And this is the real power of these local methods for pattern recognition. Okay, so in summary, I've described some local non-parametric methods for pattern recognition. This is contrary to parametric methods that imply some global functional form for the process that generates the data. Here, we're just looking at local patches of data to infer the values of the underlying function or process at some query point. And there are three different examples of this local pattern recognition that I demonstrated: k-nearest neighbor for classification, kernel smoothing and local linear regression for regression problems, and then kernel density estimation for probability density estimation tasks. The main parameter is regularization, and you can set this using a cross-validation strategy.